Okay, so think about this for a second. We are creating like so much data these days, right? It's kind of wild. Images, videos, AI models. It's like an explosion of ones and zeros, and just trying to store all that information. Right. It's nuts, processing it quickly. Well, that's where things get really interesting.
Yeah, it's crazy. It feels like this whole challenge of handling these massive data sets, it's only getting tougher. Especially with AI, everything needs more data.
Right, exactly. So what if I told you there was like this new way to like compress information, make it smaller without losing the good stuff? And get this, it uses the simplest building blocks you can imagine.
You mean that efficient one-bit tensor approximations research? The one that only uses -1 and 1? That one.
That's the one. I read through it and man, it's like something out of a sci-fi movie. Almost like they cracked some code. They're building a universal language for data, but instead of words and letters, it's just -1 and 1. It's wild.
Totally. It's like finding the absolute most basic code, like the digital DNA of information or something, and what it could do, especially for AI. Huge. AI lives and breathes on massive data sets.
Okay. So for those of us who don't speak fluent data science, here, what's so special about using just -1 and 1? Seems crazy simple.
Okay, imagine this. You're building with Legos, right?
Yeah.
But you can only use black and white bricks. Could you still build something incredible?
Right. It's just about how you arrange those basic pieces.
Right.
So instead of different colors or shapes, we've got nickel 1 and 1, the 2 Lego bricks. But how do you go from something that basic to like a super detailed image or a crazy complex AI model?
Patterns. It all comes down to patterns. And this really cool trick they call, get this, signed cut decomposition. Basically, imagine a giant spreadsheet, right? Packed with numbers. They found a way to break that down into smaller, bite-sized pieces. And every piece can be represented by those mega ones and ones.
It's like solving a giant jigsaw puzzle, but there are only 2 types of pieces. That sounds insanely efficient.
It is. What's really wild is that it might even be more efficient than some of the ways we already compress data, especially as we get these bigger and bigger data sets. This could totally change how we think about storage and processing speed,
So we're saying this could really speed things up, huh? But like, how does this signed cut decomposition actually work in the real world?
Yeah.
It still sounds kind of magical to me.
Well, it's actually pretty cool when you think about it. Imagine you have this like massive spreadsheet of numbers, right? And you need to make it simpler somehow.
It's simpler.
Yeah. So what they do is they find these hidden patterns in all those numbers.
Hidden patterns. It's like they're like uncovering some secret code buried in the data.
Exactly. That's a great way to put it. And those patterns, they can be represented by, you're going to love this, combinations of vectors.
Okay, we've got vectors now.
Vectors. But these vectors are just, you guessed it, lists of mega ones and ones.
Oh, wow. So it's like a secret language, but instead of words and letters, it's just -1 and 1.
Right. And it lets you describe something super complicated in a way that's, well, really short and sweet.
Okay, so we've got our secret language, our mega 1 and 1 Lego bricks.
Yeah.
But we're not just like randomly tossing these numbers around, are we?
You're totally right. It's not random at all. That's where the cut part of signed cut decomposition comes in.
The cut.
Yeah. It's all about strategically dividing that original matrix. The spreadsheet, they slice and dice it based on, you guessed it, the patterns of mega ones and ones.
So it's like what? Some kind of hyper-organized filing system, but instead of labels and folders, we've got math.
Exactly. It's like having this incredibly efficient librarian who just knows exactly where every single piece of information is supposed to go.
This is pretty wild stuff when you really think about it.
Yeah.
Didn't the researchers actually test this out?
Yeah.
In the real world?
They did. They used it on this large language model called Mistral-7B VO-1. It's one of those AI models that can understand and generate like human-like text.
Oh, yeah, those things are incredible. But I've heard they need a ton of computing power.
Yeah, they're really power hungry. That's why this research is so important, actually.
Yeah.
Get this, just by applying signed cut decomposition, they were able to make that Mistral model 50% smaller.
Cut in half.
Yep, 50% smaller without losing much performance at all.
That's got to be like compressing a whole season of your favorite show down to the size of like a single song.
It's crazy, right? That's how powerful this technique is. And the best part is it's not just theory. It works.
Okay, that's super cool and all, but what about something a little closer to home? I read they use this on images too, right? Didn't they even use a picture of their cat?
They did. Angus, I think his name was. They compressed a picture of their cat using this technique. And they still got pretty good image quality.
So even something as like visually rich as a picture, it can be broken down into these -1 and 1 building blocks.
Yep. It really makes you think about how we see information, you know?
For sure. It's like those artists who can do crazy detailed portraits, but they only use like dots or lines. It's wild.
I love that analogy. That's exactly right. It really challenges you to think about what's possible when you can represent something so complex in such a simple way.
This is crazy. We went from making AI models smaller to compressing pictures of cats, and it all comes down to A.W.N and 1. It's mind-blowing, honestly. But what about the average person? What does all this mean for them? Why should they care about, all this math?
Right.
It's easy to get caught up in all the technical stuff and forget why it even matters.
Yeah.
So what does this mean for, regular people? How does this impact our lives?
Think about it. Imagine if everything on your phone, all the apps, everything ran way faster, used less battery. And those giant data centers, the ones powering the internet, what if those were way more efficient too? Less energy, less strain on the whole system. That's what we're talking about here.
So faster phones, a greener internet. Okay, I'm starting to see the bigger picture here.
Yeah.
But you mentioned AI earlier, and I'm really curious about that. Those AI models are doing some pretty amazing things these days, but they need a ton of power, right, to run.
Oh, yeah, for sure. And that's a big hurdle for a lot of people, researchers, developers, everyone. But what if we could, shrink those AI models down? Imagine taking a massive program and, compressing it to the size of a normal app without losing any of the performance.
Why? So this could, democratize AI almost.
Yeah.
Make it accessible to, everyone.
Exactly. Smaller, more efficient AI that could revolutionize everything. Healthcare, education, you name it, even just entertainment, it would be huge. Suddenly, smaller companies, even just regular people, could actually use AI to do, anything, really. It's kind of crazy when you think about it.
It's like all of a sudden anyone could have access to these powerful tools that right now only the really big players have.
It's a good point. And it shows you how important it is to keep pushing the boundaries of the fundamentals, like how we represent data, a breakthrough there that can change everything.
This has been eye-opening. Seriously.
Yeah.
We're talking about Mechas 1 and 1, these super basic building blocks, and somehow we're talking about a totally different future for how we use information. It's kind of hard to wrap your head around.
And the craziest part, this is really just the beginning. We're talking about a whole new way of looking at information, not just compressing it, but understanding what it actually is at the most basic level. It's pretty exciting.
It really makes you think, what else is out there? What other simple ideas could unlock? These huge changes we can't even imagine yet. That's something to think about. And we'll be back next week to dive into another fascinating corner of the research world. See you then. Hey everyone, welcome back for another deep dive. And today we're tackling data, or, more specifically, how much space it takes up.
Yeah, huge topic these days, right?
Absolutely. Feels like we're constantly pushing the limits.
It's kind of ironic, right? Everything's digital, virtual.
Yeah.
But we're still running into these physical limitations.
Totally. So that's where this paper comes in, signed cut decompositions. I'm interested to hear your take on this. Have you ever heard of this approach before?
Honestly, not before this paper. But, that's part of what I love about this field, always something new to dig into.
For sure. So for our listeners, this paper dives into basically finding clever ways to represent huge amounts of data with way less information.
Right, and it's not just zipping a file, it's deeper than that. They're tapping into some pretty high-level math, actually. Combinatorial limit theory, are you familiar with that?
Vaguely. Reminds me of graph theory, network analysis, that kind of thing, right?
Exactly. Which seems like a far cry from, shrinking down data files, but that's the beauty of it.
Yeah, and speaking of which, I have to ask, they mentioned using this technique on a cat picture.
Right. Classic example, everyone loves a good cat pic. But seriously, it's a great way to show how this stuff can apply even to everyday things.
Okay, so less storage space, same cute cat, I'm all ears.
Exactly. They basically took this standard JPG image, right, and were able to shrink the file size significantly without, making it look blurry or pixelated.
All right, so how'd they do it?
Okay, so it all comes down to these signed cut decompositions. Basically, imagine you're building something with Legos. Okay.
Legos, I can get on board with that.
So you've got your basic bricks, right? Those are your building blocks. In this case, they're these simple vectors, and they only contain one or net of one.
Okay, I'm following so far.
Then you've got the instructions for how to put those blocks together to build something complex, right? And those are your scalar coefficients.
But instead of storing this big, complicated structure, You're just storing the instructions in the basic blocks.
You got it. Much more efficient, right?
Right, and way less storage space needed, I imagine.
Exactly. And this is where it gets really interesting, especially for like AI models, because those things eat up storage space like crazy.
Yeah, they're data hungry for sure.
Big time. And this is where signed cut decompositions could be a game changer. The researchers actually tested this out on a large language model called Mistral-7B V0.1. I don't know if you've heard of it.
Rings a bell, yeah. It's one of those massive ones, right?
It is. And they were able to compress its weight matrices, which is essentially like the core of its knowledge, by a factor of 2.
No way, they shrunk it by half.
Yep. Wild, right? But get this. It still performed almost as well as the original uncompressed version.
Okay, that I got to hear more about. So, smaller model, but still just as smart. What's the catch?
Well, there's always a trade-off, right? You can't just magically shrink data with 0 consequences. But this is where it gets even cooler. The compression is dynamic. It's kind of like adjusting the resolution of an image.
So you can choose how much you want to compress, depending on what you need.
Exactly. Higher compression means you might sacrifice a bit of accuracy. Lower compression, you retain more of the original performance. It all depends on how many of those Lego blocks you use, essentially.
Interesting. So more blocks, better accuracy, but less compression. Got it. But how do they even figure out the best way to break down these massive data sets into those blocks in the first place? That seems incredibly complex.
Yeah, good point. That's where this thing called the signed cut norm comes into play.
The signed cut norm. Okay. You're losing me a bit.
It sounds intimidating, I know, but it's actually pretty intuitive when you think about it, like a network. Like, imagine you're looking at a social network, for example.
Okay, I'm picturing a bunch of dots and lines like connections between people.
Exactly. And the signed cut norm helps us understand those connections, how strong they are, how they relate to each other.
Okay, so we're talking about relationships between people, but applying it to compressing data somehow.
Oh, it's kind of wild, right? But imagine you could, like, slice through that network, divide it into 2 groups.
Okay, I'm picturing cutting the network in half.
Exactly. The signed cut norm helps us measure how strong the connections were that we just cut. And the cool part is, this idea translates really well to understanding matrices.
And matrices are basically like the building blocks of data sets, right?
Exactly. They're everywhere.
So by analyzing these cuts, they can figure out the best way to represent that matrix with those, what were they, Lego blocks?
You got it. It's all connected. Remember how we talked about combinatorial limit theory earlier?
Yeah, the network analysis stuff.
Right. Well, the signed cut norm actually comes from that field.
Wow, so they're using tools from network analysis to compress data now.
Exactly. It's a great example of how these seemingly different fields can actually overlap and lead to some really cool breakthroughs.
Totally. Makes you wonder what other hidden connections are out there, just waiting to be discovered.
Right. And the best part is, this research isn't just theoretical, it has huge practical implications.
Yeah, especially with AI and how much data these models are using these days. It's got to have some real-world applications.
For sure. In fact, the paper actually quotes another one that describes it as a ravenous appetite for solving larger and larger problems.
Which means we need more and more data, more computing power.
Exactly. And that's not exactly sustainable, right?
Not at all. So we need to find ways to make these models more efficient.
And that's where signed cut decompositions come in. By compressing these models, we can potentially make them accessible to a lot more people.
So instead of needing huge data centers, we could run these powerful AIs on, like personal computers or even phones.
Exactly. It could really democratize access to these technologies.
That's amazing. But if we're compressing these models, shrinking them down, is there any risk of them, like, losing information or becoming less accurate?
It's a good question, and it's definitely a trade-off. But this research shows that you can actually achieve significant compression while still retaining a lot of the original performance.
Oh, wow. So you're saying it's possible to have smaller models that are just as good?
In a lot of cases, yes. The researchers actually tested it on a bunch of different tasks and compared the performance of the compressed models to the originals.
What'd they find?
The results were really promising. Even with significant compression, the models were still able to perform at a high level.
So smaller models, faster processing, but still accurate. Sounds like a win-win to me.
It could be. And I think the most exciting part is that this is really just the beginning.
So much potential here. It's really exciting stuff. But I imagine, like with any new research, there's still a lot more questions than answers, right?
Oh, absolutely. And this paper does a great job of acknowledging that. Like, for example, we've talked a lot about compressing these models, making them smaller. But what about the speed? How do they actually perform in the real world?
Right, because a smaller file size is great. But if it takes twice as long to actually use, then we haven't really gained anything.
Exactly. So one of the things they're looking at for future research is benchmarking these compressed models against other methods for specific tasks, things like matrix multiplication. Basically, it's like a speed test for compressed data.
I like that, a speed test. So they want to see if these decompositions actually lead to faster computation.
Exactly. And it's not just about raw speed either. There are questions about how these compressed models interact with different types of hardware. Can we optimize them even further for specific systems?
So like tailoring these models to the machines they'll be running on, making them even more efficient.
Exactly. And you know what else is interesting? Remember that cat picture example from earlier?
Yeah, the one where they shrunk the file size.
That's the one. Well, that actually opens up a whole other area for future research, image processing.
Oh, right. Because at the end of the day, images are just data too.
Precisely. And the unique way these signed cut decompositions work might make them especially well suited for certain image processing tasks. Think like new compression algorithms or even totally new image editing techniques.
Wow. So it's like this one concept has the potential to branch out and impact all these different fields.
Exactly. It just goes to show how powerful it can be to find these fundamental principles that can be applied across different domains. But, there's one area in particular where this research could have a really transformative impact: the retraining of AI models.
Retraining, we haven't really touched on that yet.
True. We've been talking about compressing existing models, right?
Yeah.
Making them smaller and more efficient. But what happens when those models need to learn new things?
Right, because the AI models are always evolving. They're constantly being updated with new data to stay relevant.
Exactly. So the big question becomes, can these compressed models be retrained efficiently? Can we update them without needing to go back to the original uncompressed data?
That sounds like a pretty significant hurdle.
It is, and honestly, it's one that this paper doesn't quite answer yet. It's left for future research. But if we can figure that out, it could completely change how we approach AI development, how we train and deploy these models. Imagine models that are constantly learning and adapting, but without the huge computational cost.
Now, that would be a real game changer. It sounds like this research has opened up so many possibilities. It's pretty exciting.
It really has. And it just goes to show sometimes the most important discoveries aren't about finding all the answers, but rather uncovering the right questions.
Very well said. Pushing the boundaries of what we know and diving headfirst into the unknown. And on that note, I think it's time to wrap up our deep dive for today. For our listeners who are interested in exploring these compression techniques further, you can find a link to the paper in the show notes. Until next time, keep learning, keep exploring, and keep asking those big questions.
All right, so ready to dive into something pretty fascinating.
Absolutely. Always up for a good deep dive.
Today, it's all about efficient data representation. And, it's funny, right?
With that.
We talk about too much data, but it's something everyone struggles with on a personal level too. Overflowing photo albums, those emails you just keep meaning to sort through, but they just keep piling up.
No, tell me about it. My camera roll is a disaster waiting to happen.
Exactly. But now, picture that problem, but on a massive, almost unimaginable scale, the kind of data that fuels AI like ChatGPT.
Yeah, these models need enormous amounts of data, but just storing it all, let alone processing it efficiently, that's the real challenge.
It's this constant balancing act in AI and machine learning, trying to leverage vast amounts of information without getting totally bogged down by it.
Absolutely. Finding that efficiency without sacrificing valuable insights, that's key.
And that's where this research paper, Efficient One-Bit Tensor Approximations, comes in.
Okay, I'm intrigued already. Tensor approximations sounds pretty high level.
It sounds intimidating, but stick with me. The concept is actually really cool. Imagine you're building something with Legos, right? But instead of using every single brick in the box, you find a way to use just a specific few to recreate the same structure.
Okay, I'm starting to see where you're going with this.
Essentially, this research is about breaking down complex data, these huge grids of numbers called matrices and tensors, into simpler building blocks, just using ones and minus ones.
So simplifying the data representation, making it more compact.
Exactly, and by using just those two values, you drastically reduce the storage space needed, like compressing a file, but for the very building blocks of how AI understands information.
That's a really clever approach. I can see why that would be appealing in the world of AI, where data storage is such a major concern.
So it's like we're putting these data-hungry AI models on a digital diet.
Strict one at that. But the big question is, does it actually work? Can you really simplify things to that degree without losing critical information?
Well, that's the surprising part. It seems like you might be able to. The researchers actually tested this, and the results were pretty incredible. For instance, they managed to compress a large language model, Mistral A7B 0.1, by a staggering 50%, and they still maintained really good accuracy.
Hold on, 50%. That's huge. To put that into perspective, imagine running something as powerful as, say, ChatGPT, but on your phone. That's the kind of potential impact we're talking about.
Exactly, and that's just one example. This result is a really big deal in the field, especially for large language models, which are notorious for being incredibly data intensive. Okay, so we're talking about slimming down these AI models, making them much more storage efficient. But I have to ask, what's the trade-off? We're sacrificing something here, right?
You're absolutely right to be thinking about that. There are always trade-offs. And in this case, it really comes down to finding that sweet spot between compression and accuracy.
Right, because the more you compress the data, the more likely you are to lose some of those crucial details.
Exactly. It's a delicate balance.
So how do you even begin to find that balance, that point where you're squeezing out the unnecessary data, but not losing anything vital?
Well, that's part of what makes this research so compelling. They've developed these really sophisticated algorithms that essentially act as fine-tuning instruments, so to speak. They help pinpoint that sweet spot for each data set, ensuring you're keeping the good stuff while trimming away the excess.
Okay, that makes sense, but can we maybe pull back the curtain a little bit? How do these algorithms actually work? It sounds like magic.
Think of it this way. Imagine you're piecing together a giant jigsaw puzzle. You want to see the complete picture, of course, but you only want to use the absolute essential pieces. These algorithms work in a similar way. They analyze the data, kind of like scanning all those puzzle pieces, to identify the most critical patterns and structures. Then, they use those key pieces to create a simplified representation of the data, using those ones and mighty ones we talked about.
So it's like identifying the most informative pieces of the puzzle, the ones that really make the image pop and tossing out the rest. But how do they know which pieces are the most important? I mean, data isn't exactly as easy to read as a jigsaw puzzle.
You're exactly right, and that's where this concept of the signed cut norm comes in. Now, stick with me for a second because this is really neat. Imagine having a tool, a special measuring device, that could tell you exactly how much of the picture you're losing when you simplify the data. Let's go back to that cat photo example. We want to keep those essential details, like the cute little whiskers, but maybe we can afford to lose a few stray hairs here and there.
Right, without sacrificing the overall image.
Exactly. The sign cut norm is like that measuring tool. It helps us find those stray hairs we can safely remove without ruining the whole picture.
That's a clever way to think about it. So the algorithms are using this measuring tool to make sure they're keeping the most crucial information while minimizing any loss of detail. But this brings up another question. Is this something you can use on any type of data, or are there limitations to what these algorithms can handle?
That's one of the most exciting things about this research. It has the potential to be incredibly versatile. While their primary focus was on matrices and tensors, those underlying principles could potentially be applied to a much broader range of data types.
So we could be talking about everything from creating more efficient image storage to developing faster AI processing, maybe even entirely new ways of training these machine learning models from scratch.
You got it. This research opens up a whole world of possibilities. For instance, imagine being able to run sophisticated AI programs on devices with far less power and storage, things like smartphones, maybe even wearables.
That would be groundbreaking, especially in fields like healthcare. Imagine AI-powered diagnostics being readily available in remote areas or personalized learning experiences accessible to anyone with a mobile device. The possibilities are mind-boggling.
Precisely, and we're just scratching the surface here. There's so much more to uncover and explore about the full potential of this approach. But it's important to remember.
It's almost like we're on the verge of a whole new era in AI. But with all this potential, it does make you wonder, what are the downsides? Are there any drawbacks or challenges we need to consider?
You've hit on a really important point. While the potential benefits are significant, it's crucial to acknowledge the potential challenges. One of the big questions is how these techniques will scale As AI models continue to grow larger and more complex, will they still be as effective?
Right, because the data sets these models rely on are only getting bigger and more intricate.
Exactly, and that presents a significant hurdle to overcome. Another crucial consideration is the balance between accuracy and compression. How much accuracy are we willing to sacrifice for increased efficiency?
That's a tough one. Is there a point where the trade-off isn't worth it? Where the loss of accuracy outweighs the gains in efficiency?
That's a question researchers are actively exploring. The answer likely depends on the specific application. In some cases, a slight dip in accuracy might be acceptable if it means a significant boost in efficiency. But in other areas, even a tiny error could have major consequences. Take medical diagnoses, for example.
Absolutely. The stakes are much higher in those scenarios.
Exactly. So we need to tread carefully and really weigh the potential risks and benefits. It's all about finding the right balance for each specific application.
Finding that sweet spot between efficiency and accuracy is crucial. But even with these challenges, it feels like we're witnessing something groundbreaking, a real paradigm shift in the world of AI.
Absolutely. It's an exciting time to be working in this field. It's fascinating to see how these advancements in data representation could revolutionize so many different industries.
It's like we've opened this door to a whole new realm of possibilities within the digital world. What are some of the other big mysteries that researchers are still trying to unravel in this area? What are the next steps in this research?
Well, one of the most promising avenues is pushing these compression techniques even further. How much more can we simplify the data? Can we squeeze even more information into those ones and nagus ones?
Finding even more ways to trim the fat, so to speak.
Exactly. It's a challenge, for sure, but the potential payoff is enormous.
It really makes you think, what could that kind of breakthrough mean for the average person? How would that impact our daily lives?
Imagine a world where we can store and process the same amount of data, but use a fraction of the resources we need today. Think about the implications for things like cloud computing or even personalized medicine. The possibilities are pretty remarkable.
It's incredible to consider the potential ripple effects across so many different fields. This research is really a gift that keeps on giving. Every layer we peel back reveals even more fascinating insights and opportunities.
And that's what I love about these deep dives. We start with a single topic, in this case, efficient data representation, and it branches out, leading us to explore this whole network of interconnected ideas and possibilities.
It really highlights how interconnected everything is and how advancements in one area can have far-reaching implications across multiple disciplines. Well, I think we've given everyone a lot to ponder today. We've explored how researchers are finding innovative ways to make AI more efficient, the potential this has to revolutionize various industries, and some of the exciting and sometimes challenging questions that lie ahead.
It's a field that's bursting with potential, and as we've seen, even research that might seem complex on the surface can lead to breakthroughs that touch every aspect of our lives.
It's a great reminder that innovation can come from anywhere, and that even small steps can have a huge impact. So to everyone listening, stay curious, keep asking those questions, because who knows what you might discover. That's all for this deep dive. Until next time. Ever feel like, the internet's just turning into this giant data hog?
Yeah.
Me too. But what if there was a way, what if we could just shrink those massive data sets down?
Right.
And I mean, really shrink them.
That's right.
AI models, spreadsheets, even all those, adorable cat pics we all have.
You're getting into data compression, but not the kind that slows down your internet.
Right, right.
We're talking about shrinking the actual information.
Whoa.
It's almost like magic, but with some seriously clever math behind it.
Okay, color me intrigued. So today's deep dive, we're taking inspiration from this paper. It's called Efficient One-Bit Tensor Approximations.
Yeah.
Now, I gotta admit, tensor sounds kind of like something straight out of Star Trek.
Yeah.
But stick with me, folks, because this is actually really cool stuff.
It is. It is. Imagine trying to store a whole symphony, all the music, right?
Okay.
Instead of keeping every single note, what if we could just break it down into simpler instructions?
Interesting.
A kind of musical shorthand. That's what this paper's doing with data.
Musical shorthand for data. Okay, I kind of like the sound of that. So let's unpack this a little bit. They call it signed cut decompositions. Can you break that down for those of us who, maybe slept through calculus?
Sure. Imagine those plus and minus symbols back in grade school math.
Yeah, the good old days.
This method uses those plus and minus ones, and it combines them to approximate the data.
Hmm.
Sounds strange, but it can recreate some crazy complex stuff using that simple system.
So instead of storing every detail, like every brushstroke in a huge painting,
Right.
we're basically making a recipe
Exactly.
that lets us recreate the image really precisely, but just using like a few basic ingredients.
Yep. And the best part, as the data set grows, the accuracy actually gets even better.
Oh, that's counterintuitive.
It is, right. They even tested it on a massive language AI.
What, like one of those AI models with billions of parameters?
And get this,
Okay, hit me with it.
they compressed it by 50%.
No way, cut it in half.
Cut it in half while keeping the errors under 6%. Imagine like cutting a powerful AI's brain power in half and it can still do its thing.
That's incredible.
50% reduction for a tiny 6% dip in accuracy.
Yeah.
That's huge.
That's like finding out you could fit your entire music library on something the size of a postage stamp with like barely any loss in quality. So we're not just talking about like zipping files here.
This is different. This is about understanding the fundamental structure of the data and how to represent it in the most efficient way. Traditional compression often loses stuff, you know.
Right.
This preserves the essence of the information.
Okay, so they proved it works. But let's talk about something a little more, I don't know, relatable.
Okay.
What about something like your camera roll full of photos?
Ah, yes. Your cat photos are safe, I promise.
Okay, good.
They actually show how this can be used on more than just numbers. Images, when you really boil them down, they're just grids of numbers, right?
Yeah.
Representing colors.
So my cat's adorable little face is actually a tensor.
In a way, yes. A tensor is just, well, it's a fancy way of saying a multidimensional array of numbers. It's like that grid, and each cell has info about the color of that pixel in the image.
Right, okay.
The paper actually looked at a couple ways of compressing image tensors, RGB signs and RGB scalars. Turns out, scalars were better. It's like finding the most elegant way to describe a color.
So you're telling me my cat photos can be even smaller and cuter?
Potentially, yes.
This is amazing, but I have a feeling this is just the tip of the iceberg, isn't it?
Oh, absolutely. This is really just the beginning. There's so much more to explore.
This research opens up so many possibilities, and it feels like even more questions pop up, which is honestly incredibly exciting.
Okay, so we can shrink our cat photos. Cool. But let's talk bigger picture for a sec.
Where else could this tech, like, really shake things up?
Imagine, right, you're scrolling through social media, and bam, this cutting-edge AI just generates a personalized meme right there on your phone.
Okay.
No lag, nothing. All because of this compression, you know, making the AI smaller, faster.
No more waiting for things to buffer. I
Yeah.
mean, I'm sold already, but seriously, right now it feels like you need a supercomputer just to run some of these AI models.
Right.
This could make them way more accessible.
Exactly. And it's not just about AI either. Think about all the data centers, right?
Yeah.
Giant warehouses
Yeah.
full of servers, just eating up energy.
Oh, yeah.
This tech could really slash that energy footprint, make data storage massively more efficient.
See, that's huge. We're talking about like tackling climate change with compressed data.
Potentially, yeah. And here's where it gets even wilder. Imagine training the AI on already compressed data.
Whoa.
So instead of all the raw info, it's getting this efficient compressed version.
So we're like teaching AI to speed read. Would it actually learn faster?
That's the million-dollar question.
Mm-hmm.
Researchers are digging into it right now. If we could figure that out, it could change everything. We could be training way more powerful AIs, but in a fraction of the time, all because data size isn't holding us back.
This is blowing my mind. It's like we're not just making data smaller, we're changing how we even think about information itself. Like, what are the essential parts? How much can we strip away and still keep the meaning? It's almost philosophical.
It really is, and it makes you wonder, you know, about the nature of reality itself. If we can take incredibly complex stuff and represent it with like pluses and minuses, what does that tell us? What if the universe is just this like really efficient compression algorithm?
Whoa, okay, you're going deep on me now. Are you saying we're all just living in a simulation?
I wouldn't go that far.
Yeah.
But it does make you think, doesn't it?
It does. It really does. So to bring us back down to earth for a minute, what should our listeners like take away from all of this?
I think the big takeaway here is we're on the edge of a major shift in how we deal with data. We're creating more information than ever before, and this research, this gives us a powerful tool to manage it.
It's not just about making things smaller. It's about understanding those fundamental building blocks of information, and that has huge implications. AI, data storage, even maybe our understanding of the universe itself. So for our listeners out there, the ones who are ready to, jump in and start compressing everything, where do we even begin?
Right.
What are the big unanswered questions, the next frontiers in this whole tiny data revolution?
Well, I think one of the most exciting things is we got to figure out just how far we can push this compression thing.
Okay.
The paper, they focused on one type of AI, right?
Yep.
And a few examples, but there's a whole universe out there, each with its own, quirks, challenges.
So it's like they've given us this incredible new tool, and now it's up to everyone else to figure out what we can build. But what kind of tools are we talking about? Give me some specifics.
Well, for one, we can always make the compression itself better, right?
Yeah.
Can we find even more efficient algorithms? Can we tweak the approach for certain types of data?
Oh, interesting.
Like audio, video, even like the genetic code in DNA. Imagine if scientific discoveries just happened way faster because we could analyze huge data sets.
Yeah.
Like that.
It's like having a specialized compression tool for every occasion.
Exactly. And as we get better at this, think about storing and sharing info.
Okay, yeah.
We could have devices that hold libraries worth of stuff or send information across the globe instantly.
That's mind-boggling. But all this talk about shrinking things makes me wonder, is there a limit? Like, can we just keep compressing forever? Or do we eventually lose something important?
That is the question, believe me.
Yeah.
It gets to the core of information theory, right? What is information, really? And how do we represent it in the most efficient way possible?
It's like trying to find the universe's own compression algorithm.
Exactly.
Wow. Well, on that note, listeners, if this deep dive has, piqued your curiosity, let us know. Head over to our website, find us on social media, share your thoughts. And until next time, keep diving deep. Ever feel like we're just drowning in data these days? Seriously, pictures, videos, apps, it's like you can never have enough storage space.
Yeah, it's kind of wild how much we rely on digital stuff now.
Totally. But what if there was a way to shrink all that information down? Make it, way more manageable?
Okay, now you've got my attention. Sounds like something out of a sci-fi movie.
Well, that's what today's deep dive is all about. It's a new mathematical technique for compressing data. And get this, it's not just about making files smaller. It could totally revolutionize artificial intelligence.
All right, you're speaking my language. Tell me more.
So this technique, it's called signed cut decompositions.
Signed cut decompositions. Catchy.
I know, right? It sounds way more complicated than it actually is.
Well, hopefully you can break it down for us.
Absolutely. It's all about tackling data overload, right? Like we're creating information faster than ever before.
And all our old ways of handling it are struggling to keep up.
Exactly.
So how do these, what was it, signed cut?
Signed cut decompositions.
Right, so how do they actually work?
Think of it like, imagine a massive spreadsheet. Just completely filled with numbers.
Yeah, okay, I'm picturing it rows and rows of numbers.
Exactly. So this technique basically takes that giant mess of data and breaks it down into smaller, more manageable chunks. And it does it all using just Magus 1 and 1.
Wait, hold on, just Magus 1 and 1. How do you even represent anything complex with just those two numbers?
That's the crazy part. It's about finding hidden patterns, those underlying structures within complex data, and then representing them in the simplest way possible.
I guess I can see how that might lead to some serious compression. But, how effective can it really be?
Well, the research paper we're looking at today, they actually used this technique on an image of a cat.
A cat, huh? Always gotta love a good cat picture.
Right. And get this. The results were surprisingly accurate. They were able to compress the image significantly, all by breaking it down into a pattern of mega 1 and 1s.
Okay, that's actually really cool. I knew compression algorithms are getting good, but to represent a whole image with basically just two values, that's pretty wild.
It really is. But what's even more impressive is how they applied this to a large language model, specifically one called Mistral 7B V0.1.
Okay, I'll be honest, large language model, that's a bit over my head.
Basically, think of it like a superpowered chatbot. It's trained on a huge amount of text data and can do all sorts of crazy things like generate human quality text, translate languages, even write different kinds of creative content.
Whoa, so we're not just talking about compressing cat pictures anymore. This is some next level stuff.
Exactly. And these models are incredibly complex, require a ton of computing power to even function.
Yeah, I can imagine.
But here's where it gets really interesting. By applying this signed cut decomposition, they were able to compress the model's weights, basically, giant matrices of numbers, by up to 4 times.
4 times, that's insane. But I have to ask, what about the model's performance? Did it actually still work as well after being squeezed down like that?
That's the real kicker. They managed to achieve this incredible compression with minimal impact on the model's performance.
No way. So you're saying they shrunk this incredibly complex AI down to a fraction of its size, and it still functions practically the same.
That's exactly what we're saying.
Now that's a game changer. This has got to have some huge implications. I mean, think about what we could do if we didn't have to worry as much about these limitations with AI and data processing.
You're preaching to the choir here. What if we could have AI as powerful as today's supercomputers, but running locally on your phone, making decisions in real time?
It's like the future just landed right in our laps.
Okay, but seriously, AI on my phone that's as smart as like a whole supercomputer, it's kind of hard to wrap my head around.
Yeah, I know what you mean. It's definitely exciting stuff. But we should probably pump the brakes a little. This research is still pretty new.
Right, right. It's not like we'll be seeing super smartphones tomorrow, I guess.
Exactly. There are still some challenges, like this technique seems to work best on certain types of data, like those massive matrices they use in AI models.
So it's not a magic compression solution for everything just yet.
Not quite. They're still figuring out how to apply it to other kinds of data. It might take some tweaking.
Makes sense. And what about accuracy? You mentioned the language model's performance wasn't affected, but is that always the case? Like, is there ever a trade-off between making things smaller and losing information?
That's a really important question. And the answer is, yeah, sometimes. There's often a balance to strike between compressing data and maintaining accuracy. You squeeze something down too much, you might lose some detail. The trick is finding that sweet spot, the level of compression that gives you the biggest benefit without sacrificing too much information.
Finding that perfect balance, right? So we've talked about the potential, the challenges, but are there any downsides we should be thinking about? I mean, this feels like the kind of tech that could have huge implications.
You're definitely right to consider the bigger picture. This technology could completely change how we interact with data, and that means we need to be smart about how we use it.
Okay, I'm listening.
For example, if we can suddenly store way more data in the same amount of space, well, that raises questions about privacy and security. We need to make sure those things are addressed, that we're not just making it easier to collect and store tons of information without proper safeguards.
Yeah, that makes sense. It's like any powerful tool, right? We have to use it responsibly. But speaking of big impacts, what about the whole, robots taking over the world thing? This feels like the kind of tech that could lead to a lot of automation.
I get where you're coming from. It's a valid concern. But personally, I see it more as an opportunity for transformation, not replacement. Just like the internet changed the job market, this kind of technology could lead to new roles, new industries that we can't even imagine yet.
So less about humans versus machines and more about humans and machines working together.
Exactly. This could be a big step toward that kind of future.
I like that. Okay, so we've talked about the potential, the challenges, the ethical considerations. But before we wrap up, I want to circle back to something you mentioned earlier. The researchers hinting at applying this to like all sorts of different data types. What are your thoughts on that? What kind of crazy possibilities could we see if this thing really takes off?
Honestly, it's where things get really mind-blowing. The paper actually mentions trying this on other data, even stuff that's already been compressed.
Wait. Compressing something that's already compressed? That's like, I don't know, folding a piece of paper in half over and over. Eventually, you just can't fold it anymore.
It feels like that, right? But mathematically, there's still room to play with. Even compressed data can have patterns this technique can use.
This is why I love these deep dives. It completely changes how you see things. But okay, give me some examples. What kind of applications are we talking about here?
All right, buckle up. Let's start with something like, imagine scientific data sets. Huge amounts of information, shrunk down to fit on your phone. Scientists could access all that research instantly.
Whoa, that would revolutionize research.
No more waiting for giant files to download. That's just one example. Think about entertainment. Imagine video games, but like hyper-realistic, or those VR experiences everyone's talking about.
Okay, you're painting quite the picture here.
All that stuff relies on massive 3D models. But if you could compress them down, we could have crazy immersive experiences without needing like a supercomputer to run them.
So not just faster, but more accessible too. Man, we started with compressing cat pictures, and now we're talking about revolutionizing entire industries.
That's the thing about these new techniques, right? They pop up in one area, but the ripple effects, they can be huge.
It just goes to show innovation can come from anywhere, and even the most complicated ideas, with a little digging, they're not that hard to understand.
Exactly.
So to everyone listening, we'll leave you with this. What other uses can you imagine for this kind of compression? Hit us up on social media, let us know your thoughts. Until next time, keep exploring, keep learning, and we'll see you on the next deep dive.